Good morning. I have 4 handouts there. 2 of them were the exams from last 2 semesters, last 2 years, right? There's no reason why we should have the same kind of exams or whatever, but they'll give you a sense of what kind of questions you'll get asked, right? And I'm going to go through a little bit of like overview and sort of answer the questions about from the survey. Is it too loud? Okay. So far 20 of you have answered, and I think there's some bug in the survey monkey or whatever, because for example for the first question it thinks 10 people answered 2, 10 people answered 3, and 1 answered the first one, but the sum is 20, right? I wonder if there's a race condition inside, right? So in terms of the question about harder, I think it's sort of like half and half. And in terms of the work, I think a third of you seem to think it's more than expected. The others seem to be okay with it. The pace and everything. Too many of you don't seem to like the course yet, right? So one of the comments was interesting to me, because it if it is true, potentially there may be a problem with the way things are done, right? So modules 1 and 3 and 4 are hardcore operating systems. Module 2 that we spent a whole bunch of time, it's a little bit operating system, but mostly because the programming aspects of what happens because of a operating system abstraction called threads, right? So this comment basically said, they understood, I'll let you read the stuff, but people understand what operating systems are, like sort of like Windows XP or Mac or Linux or something. So they have a tangible sense of what operating system is. And all the things we've been covering in module 2 seems to be sort of like abstract, theoretical kind of stuff, right? And having a code example would help make this stuff clear, right? And before we show code and stuff, I want to make sure that people understand what an operating system really is, right? You had a chance to read the comment, right? How many of you agree with the stuff that as a CSE students you have some sort of a grasp of what operating system like Mac or Windows or something is, right? At least to a large extent. I mean, you've been using the machine for a while, so you kind of hope that you know what it is, right? So do you, right? What is an operating system, right? When you log into a Mac, sort of like you log into a Mac or Windows or whatever, you have like sort of like, the screen up there, Windows up there, and if you press like, certain buttons, the Windows closes and you open some things. You see a visual sort of sense of how you interact with the machine, right? It could be as primitive as like a DOS kind of screen where it's a command line prompt, or it could be a GUI kind of based interface. I mean, when you log into Windows, that's the persona you see. You don't see the non-GUI kind of stuff, but you see a GUI kind of approach, right? You see a windows and screens, and you can click certain things to open a new application, click certain things to close application, certain keystrokes to do certain things, right? Right? This is what you see as operating system, right? Is that the operating systems? What is it that you're seeing? What is it that you're interacting? Yes?
The UI. Just in general.
Yeah, so what is the UI in the grand scheme of things, right? So if you look at the sort of I think we started off in the intro, right? So if you think of these as sort of layers, you have a hardware, right? Like sort of your processor or memory and all those things. Then you have some sort of a firmware. In a Mac, it tends to be EFI or BIOS or what have you, right? And then you have the operating system, right? Which actually, in the Mac case, it's called XNU. That's what they kind of use with. And then you have these systems programs on top, right? And one of them is this GUI application, which gives you the stuff that you work with. And you have the applications, you have the PowerPoint or what have you, right? And this is sort of how it is done. And we kind of mentioned this before, but essentially from here to here is a device driver interface. You want to have some sort of a device driver in the operating system which talks to the devices. And on the top, you have some standard APIs like POSIX, right? And you use a system call to access those things, right? So from an operating system perspective, you have POSIX talking to the upper layers, and you have device drivers talking to the lower layer. And it could be IDE, SCSI, or what have you, right? To make it a little bit more concrete, I don't know if you can see the whole picture from the back, right? This is the structure of Mac that Wikipedia has a nice image of this, right? So if you look at this, there's the hardware, right? And then there's this thing called kernel whatever. At some point they call it Darwin, right? But there is this notion of IO kit and drivers which talks to the hardware. And there's file system networking and kernel, right? Which is what we have been focusing, we focus in this class, right? And on top of that, you have system utilities, and you have core. And then way up at the top is Aqua, which is what you see as a GUI thing, right? So when you log into a Mac machine, you are logging into Aqua, which calls the Cocoa framework, which calls the core services, which calls something. Eventually, it goes to the operating system, right? The flip side of this is, do you believe that Macintosh, Apple can replace this operating system with Linux and still be able to have the same look and feel as you're used to in a Mac? Is that possible? I'm not saying whether they can do it immediately, but with some effort, can they do that? They ought to be able to, right? You don't, if they remove this and put a Linux in there, as long as they get all the system calls they need to do the upper level services, you will know a difference, right? They can do that for any operating system, you can do that. So in Windows, when you log into a Windows machine, you're logging into Win32 API-based applications, right? And that eventually does a lot of stuff, and then it calls the underlying operating system, right? The only way that you can interact with the operating system is through a system call, right? Or through utilities which call system calls on your behalf. And only those have to change. They can remove this and put whatever they want, and you won't know a difference, right? And you may notice it. So there are two open source operating systems, Linux and FreeBSD, right? If any of you have installed or played with FreeBSD, you'll notice that FreeBSD looks very much like Linux, right? Because FreeBSD and Linux uses GNOME Window Manager, which sits on top of those. So unless you really unless you really like some system calls, you won't know the difference, because from your perspective, they look the same, right? When you buy something from Microsoft or Apple, they don't differentiate those. They don't say, we are selling you Aqua with all the marketing jargon they have to sell this. They just say, this is Mac operating system, right? And in terms of what really happens, these things don't change as much as they would like you to think, right? Operating systems barely change across these different versions, except you tweak certain things. So if you have Windows 2000 or Windows XP or Windows 2003 or Vista or whatever, whole lot of things changes at the top, right? Your GUI looks different, you have like nice screen and all those things. But chances are your real operating system might have barely changed, if at all. I mean, they may have tweaked it to make it more threaded, they may have tweaked it to make it more responsive or whatever, they may change the scheduling algorithm or whatever, but the changes that happen here are minimal, right? And many of us, including me, don't really know what is happening here, and we don't buy an operating system based on this, right? How many of you think after this course you're going to ask the vendor, it's fine, but for interactive tasks, do you run first come first serve scheduling, or do you run round robin, right? How many of you are going to ask the stuff, right? You don't ask the stuff because those are all kind of in there, right? But as students who are taking operating system, I want you to be aware of what is happening. I mean, so what we look at here is sort of abstract. It's sort of, you don't get to see it, right? You may see it a little bit more than you notice that you're running on a hardware, right? So how many of you notice that you're running on a x86 or a PowerPC or Sun machine? How about
Indianness for
when you program, right?
yeah.
Yeah, when you program, when you start to do system calls, when you start to do stuff, you notice, right? So if you're operating on a 64-bit machine, 32-bit machine, you notice the difference, right? Your Indianness makes a difference. It should make a difference if you're programming simple programs. If you're doing integer programs, you don't notice it. But if you're trying to do kind of weird stuff by looking at what order it's stored on memory and all those things, you start to notice it, right? So it's sort of similar to that one, right? It's still sort of abstract. It's not really abstract because you ought to know what things are happening here, but that's an important notion, right? I usually bring this up in the last module because I want people to be aware of what is operating system, right? There's a big fight. I don't know how many of you are interested in the Linux versus Windows argument, right? There are people who like Linux who think that Linux is a thing that's going to solve whole bunch of problems. There's people who hate Windows and stuff, right? I think a lot of them miss the point that the operating system component, right, of Linux and Windows, it's fine. Most of you don't buy Windows because of the operating system. You buy it because of the stuff on top, right? And that's the part which Linux has to implement. Linux has to do that, and that's the part which adds value, right? If you just get the raw operating system, it does practically nothing, right? And the whole, so Microsoft's main selling point is things up there, not up here, right? Obviously, this has to be good for them to work fine, but they're not selling Vista because the core scheduler changed from O of n to O of n squared or something. They're selling it because they have all these APIs, so you as a programmer can make these programs a lot simpler. You have all the support. So if you wanted to, for example, in that module, you see a big thing called QuickTime, right? So on the Mac, if you want to do a video, it's very easy for you because something called QuickTime framework gives all the stuff for you, right? So you as a programmer care about that part, right? So that brings up the question, what class do we teach which covers those components, right? Do you know of any course we teach which really covers those components? Unfortunately or fortunately, we don't, right? We don't teach a course like that, right? So we kind of, it's something you'll sort of learn on the job. The assumption here is there's really nothing earth-shaking there. It's just to learn how to write big programs, right? I think you're going to have one program that Professor Flynn is teaching, I think, programming paradigms or something, which will teach you how to program in large systems, right? But for the most part, we kind of ignore that because it's considered to be a lot of big programming, and you'll kind of learn that on the job kind of thing, right? Does it make sense, right? So, I'll give you some source code examples of what happens in the operating system, right? And most of the time, the code is pretty trivial, and most of the times the code is so horrible that I don't want to bring it up till module 5, if at all, right? Even though you would like to see the kernel, which is exactly what you did for the homework project. How many of you actually went through the kernel code to see what is written there? You're compiling the kernel, right? Did anyone go through the source code? We will look at it a little bit later on. You'll find that the code is very simple because it has to be simple because you want the things to be predictable, fast, and everything, right? But it's not designed for novice programmer, right? I'm not sure how many of you know good C programming, but I'm talking about real good C programming, right? You have to be exactly aware of what you're doing because these are critical systems, right? And one of the things you learn from the course project, so I think one of the comments asked was, can I give hints on what threads are and what causes problem, right? And I think one of the email I sent yesterday or so was about this scope, right? How many of you remember seeing that mail about scope, right? When you have a C program, you have to be aware of the scopes and stuff, right? This stuff you probably learned in the 220, right? The first programming class, right? All you're noticing is all the things you learned before, all the things you thought you knew before, if you're not very careful, comes back to bite you, right? One of the things which happen is once you look at all the thread programming, I'm kind of jumping ahead a little bit, but once you look at the thread programming, how many of you done with the project for the second project, right? Once you look at that program, right, once you start to debug those programs, right, if you kind of know how to debug those programs, your whole segmentation fault error that you probably had from your first programming class, which you probably thought was a hard problem, is you realize it's not at all, right? If you get a segmentation fault, that's the easiest problem to solve, because it tells you exactly what's going wrong, right? You may not know at this point how to use a debugger, but once you do use a debugger, segmentation fault is the easiest problem you can ever solve. The hardest problem to solve is using threads, right? And that's why we are kind of struggling in this module, because threads introduces timing issues. That means you need to understand exactly what the program does, right? And if any of you don't understand how exactly a program works, you run into a problem, right? So let me give you an example, right? So how many of you follow this case, okay? You kind of have a large C program. At some point, you expect the value of I to be from 0 to 100, right? You wrote the program so you know what the logic should be, so you expect the value to be 0 to 100, right? And you run this program for 50 different cases, and one case, it seems to fail, right? One case, you put a printf statement, you say printf of I, and you notice that for one particular case, the value of I happens to be -2, let's say, right? And your project is due in like half an hour, or this is like 3 o'clock in the morning, right? How many of you wrote a code that says if I equals -2, I equals 0, and then compiled it, it worked, and you got the answers? How many of you done this? Or how many of you would do this? And how many of you would actually sit down and figure out what exactly happens?
Depends on what time it is. If I have time to do it, then I would try to figure it out. But if it was due tomorrow and it was 3 a.m., I would totally just mark code the 2 in there.
Yeah, I mean, I suspect all of us would do that, right? I mean, if it seems like you kind of know that it doesn't only work for this particular case, so you hope that the instructor does not try to look at what happens if I equals 200, right? It might fail, but for the most part, it seems to work, and everything works fine. You're kind of done with it, right? Which is sort of where I assume your programming skills are at this point, right? You cannot do something like this if you use threads, right? That's one of the things you kind of realize, right? Because when you have threads, you essentially have multiple threads doing something, right? If I happens to be -2 here, that could either be because something benign, something like where you calculate I was kind of wrong, or because there's some other thread which is writing something which is modifying the I to be -2, right? Which is a timing error, right? Which means that if you run it 100 times, sometimes it can be -2, sometimes it can be -1, sometimes it can be 0. So in that case, this particular fix won't work, right? Which what is really happening is some other thread is modifying I. So even if you make I equals 0, the immediate instant after that, the other thread can modify I back to -3 or whatever, right? So you can't really debug these. So you really have to understand what your program does. You really have to know what your program does. So all the things you learned from your prior programming classes, it's the same thing. You still have the same bug and everything, but in the prior classes you can kind of do this stuff and then get away, right? Don't be too ashamed, because you see this in production code too, right? If you look at some production code, somewhere deep in there, you'll see one comment that says, "Do not touch the next line," right? And after a few years, everybody forgets why it's there, right? But the comment will say, "Do not ever touch this, because if you touch this, things will go wrong." No one figured out what it is, and by the time the code has become larger, you kind of leave it, right? So when you guys go into work on large projects, you'll see these little nuggets which says, just leave it like that, right? You can't have things like that, right? And so that's one of the reasons why my colleague from Apple was saying that if he talks to you and if he gets a sense that you understand synchronization primitives, then he can hire you. He doesn't care whether you know databases or compilers or what have you, because he kind of assumes that you know how to do good programming, right? The flip side is, this course is not set up for you to achieve that level of competence, right? Because we're just going through this for a little bit, and this is an ongoing process. As you debug, as you go through these things, you'll learn the stuff. So hopefully the homework project 2 helps you, right? So I'm not sure how much I can help you by showing you programs in the class, especially since we have a small time, right? But if anyone wants to go beyond what we had, and they want to suggest changing homework 2 or 3 or something as extra credit to try something really more beefy than the homework project, right? Some of you who are doing the homework project realize that it's not as complicated as it might sound, right? You can sort of do it intelligently and get away with a whole bunch of complicated stuff. But if you want to try more stuff, that I'll be free. I'll be glad to work with you. But it's not expected to be simple, right? So the second module is not expected to be simple because it's part of a larger problem that you'll face throughout your career. So going back to the so we are going to focus on this one, which is not exactly the glamorous part, because that's not where all the windows and all those things happen. This is where the other stuff happens. So what really happened so far was in module 1, right? We did the hardcore operating system part, which is we kind of defined a notion of a process, which seems so natural, right? So a process is a program in execution. If you have a program, it has to be called something, and we call it process, right? And we have some data structures called PCB and all those things, so our operating system knows how to deal with that. You have a sense of which process to schedule, all those things which follow rather straightforward, right? But we also noticed that the hardware trend is to have multiple processors, in which case the application said they wanted these processors to be assigned to the application. So we created the notion of threads. We assigned multiple processors, right? And that's where the operating system ended, right? Right? So that is the module 1, like one we looked at last module, right? And it's fairly trivial because it's obvious, right? Because there's no other way you can do that. I mean, you have to run a process. You have to run a program. So you have to call it something. Let's call it process, right? And you have to schedule them because there's multiple stuff of them. Multiples of them. You want to schedule them. That's fine. And you wanted multiple processes. Here I give you multiple processes. Call it thread. Operating system job is done, right? But turns out that it's not that simple, right? If I just give you multiple processors through a thread, right, as operating system, and leave it up to you, there are some cases where you couldn't proceed as a programmer, right? So all the things we looked at in module 2 is essentially the problems that you will run in as a programmer, right? From an operating system perspective, we don't particularly care what you run into because it's your fault, right? Because you don't know how to write a good program or what have you. But in practical sense, the problem came about because I gave you multiple processors through threads, right? So the whole notion of critical section was we are showing that there are some applications where the threads make no difference at all. The threads seem to be fine. I can give you any number of threads. You are fine. But for some cases, if I give you threads, you notice that the program is no longer behaving in a certain nice fashion, right? And that's the notion of a critical section, right? And when that happens, right, we can solve the problem by saying everything runs at a predictable fashion. So I can say each thread will get to run, I don't know, one instruction before going on to the next one. So if I make it all predictable, then you could solve that, right? But you don't want to do that because if I do that, then I can't assign you some slack. So if I have an extra processor, I can't just give it to your application because now you're saying it has to go in a certain fashion. You want the timing guarantee, so you want if it things to be predictable, right? You are restricting yourself. So you don't want that. So how do you get all these things to run in parallel and still get good performance is the notion here, right? And again, this has nothing to do with the operating system. So as operating system, we don't particularly care. I gave you threads, right? It's up to you to make sure that you define this notion called critical section in a program, right? Me as operating system has nothing to do with it. You define in your program what is a critical section. If you don't, if you have multiple processes, you will run into a problem. That is what we mentioned here. And the solution does not have to depend on the operating system, right? And that's the key thing you have to remember. But we define all this notion of conflict seriousness between all those things as a programming concept, right? You as a programmer has to be aware of all this stuff. And if you're aware of this stuff, then you can use the services provided by the operating system, which is the thread, and still be able to get the performance that you wanted, right? So in a strictly pedantic sense, this does not belong in operating system, right? Like the module 2 does not belong in operating systems because, hey, I mean, you ask for a thread, I give you a thread, that's it, right? If you run into problems, that's why is that my concern, right? Would you agree with that logic? Can I say, it's not my problem, right? You ask for multiple threads, and if you've done it a problem because of using multiple threads, why is it that I as operating system should do anything about it, right? Yes?
Because the programmer can make a big enough mess and bring stuff down. I mean, it's not like you can just play in a little sandbox and call it good.
Yeah. Part of the answer is, you can't really say that. Part of the answer is, I want you guys, right? I mean, if I'm an operating system, I want the application developers, right? So Microsoft does not say, we're going to do this. If you don't know how to program, go away, right? Because we're all in this together, right? We're all partners, right? Application developers and the operating system and the hardware are partners, right? Maybe Intel does not come and talk to you for, take you for lunch and ask you what should we do, right? But essentially, we're all partners, right? Intel has lunch with the operating system folks. Operating system folks have lunch with the developers. So we all want to make this happen, right? So we don't have this ideological warfare where we say, this is not an operating system, we don't care, right? We want to help, we want to solve it. And that's why we're kind of looking at this, because we're like, it's your problem. We'll help you where we can, but for other stuff, it's up to you, right? So we're telling you, you're going to run into the problem of critical section, right? It's up to you to define what a critical section is. It's up to you to solve it. I may help you with giving you some primitives which will help you. I'm not going to solve the stuff for you. I'll give you some primitives, right? And the first way we looked at the critical, we said there's a bunch of conditions which have to happen for critical sections to be valid, right? And we talked about how to solve them, right? The first notion was the test and support or swap, right? So essentially you can use that to solve critical section problem, right? So do you think it's possible to solve critical section problem without involving the operating system? Do you need to, does the operating system have to get involved with this? Since the hardware supports the test and set or swap, right? Why am I getting involved with this problem, right? Why don't you just program it in test and set or swap instruction? Or can you? Right? Do you have to ask something from the operating system, or can you do it yourself? I think the answer was in the book, right? Which is you can solve it yourself. You don't have to ask the operating system for help, right? The operating system. So if you use the test and set, if you can program in assembly language or whatever to make sure that the test and set gets run, then you could do the same thing, right? You don't have to ask the operating system, right? Where the operating system can help is if you have to be blocked, right? If you're going to be waiting on something, right? You as a program cannot say, I'm going to put myself to sleep, right? You're going to have to go away for sleep. You can't just go to sleep. You have to say, I'm going to sleep waiting for this condition, right? So when that condition happens, you have to wake me. So that means your process has to go from running to wait state. And the operating system has to know that you're waiting on something, right? And that's something, so that means the whole operating system gets involved, right? Because it can only put you on another wait queue if it knows what you're waiting on and when to wake you up, right? So other than that, you don't have to ask the operating system. If you're willing to spin, right, which we noticed that for the single processor case, it makes no sense. But if you're willing to do that, then you don't have to get the operating system involved at all, right? But getting the operating system involved makes things nicer. So when you know that you're waiting for somebody, you can tell the operating system, I'm going to go to sleep. I don't know who I'm going to be woken up by, but I'm waiting for this condition, right? So that means the case where somebody raises a condition will also have to be known to the operating system. So that's where the operating system gets involved, right? So it provides you with this mechanism. It provides you with the semaphore and all those things, some primitives, because it can make these things go. You can still get this functionality before, but now it can be more elegant. I can actually put you to sleep rather than you spinning on a log, which we kind of looked at as a bad thing, right? So that's where this whole notion fits in, right? You as a programmer will run into critical section, and I as operating system will try to help you with these little solutions, but the real essential problem, even these tools will not solve you, will not make the problem go away. You still have to do something else, and we'll see that in the next thing. Okay, so I actually have it here, right? So the first notion is notion of critical section, right? So we solved that with the semaphore, right? Then we saw that even if you have a critical section, even if you have these locking primitives, there are some conditions which is more complicated. The notion of a deadlock, right? The deadlock happens even if this again happens in your program. Even if you use critical section, there could be cases where deadlock happen. And so we talked about a number of ways of how to avoid, prevent, and all those things. And in those cases, the operating system could be involved, right? Traditionally, operating systems are not involved with those, but I maintain that in the future, your future operating systems will be involved, right? Because what's going to happen is you as a programmer are going to shoot yourself in the foot and get into deadlock more and more often. So you are going to complain to Microsoft, and Microsoft, you are the customer, so you can't say, we don't care, just go away. They have to try to solve this. So it essentially has to go in, right? The reason it has to go in is more and more of you are going to use multi-threaded programs, which is going to run into these problems, right? And you can't continue to say it's not our problem anymore, right? And that's the notion here. So in terms of looking at source code, right? One of you mentioned, I don't want you to try to understand this code, right? Some of you may understand this code because it's fairly trivial. Some of you may not understand what this code does, and that's perfectly fine. We'll try to look at it at the end. Within an operating system, this is the code for locking, right? So I'll explain this, but if you don't understand, that's okay, right? This is C. So it tries to, when you try to do a mutex lock within a Linux, this is from Linux kernel. So if you look at the Linux source code, I think if you look at AR, like in your kernel directory, ARCH/IA86_64, right? Under architecture directory for 8086, like internal architecture, you'll see the code for this, mutex.s, I think, right? So essentially it says that it's going to lock it, when you want to lock something, it's going to try this assembly code, and if it's going to wait, right, it's going to call that function, which is a slow path, which means it blocks you. So essentially what it's trying to do is, it's trying to see if it can spin or if it has to be blocked, right? So this is assembly code. How many of you program with assembly in C? If you haven't, right, from assembly you can call C easily, right? Sorry, from C you can call assembly very easily, right? So essentially if you follow this, right, so this is the assembly code to do the test and set, right? So it's trying to do a test and set up here. If you don't follow along, that's perfectly fine. But essentially it's calling the test and set conditions for you, and if something happens, it says call this function, which is what you call, right? So if it has to be blocked, it goes into some other mode. If it goes to some other mode, right? So this is exactly what the code is inside the kernel, right? But I don't think that's what you mean by looking at what the kernel does, right? Because this is conceptually what test and set does. I mean, you're looking at the big picture, not the core details, right? I'm going to change it before we get lost on that part. So does that make sense, right? So this module is unique because it's kind of partnership between programming and the operating system. And we broke it, so we're trying to help you with some ways to deal with that, right? And essentially the problem is a problem which happened because of that, so we're trying to solve it. And semaphores and other things are good abstractions for solving this problem. And again, these things are good programming practices, right? So think of these as programming mechanisms that you use, sort of like a recursion, right? You probably went through recursion in your programming class, right? It teaches you that this is a way for you to call recursion. This is what might happen. What is the problem? What is how you deal with those? And these are examples of those. These are good programming examples, which you will do it in your own program, and some of them create some problems. Like for example, if you have a dynamic philosopher-like system, you will run into a case of, you might run into deadlocks even if you have a critical section, right? And that's sort of the trend of what we looked at, right? Again, these are all problems that you learn it as a programmer, and here is some ways you may solve those, right? And we want to work with the operating system and the programmer, right? And the last, so how many got confused with the notion of atomic transactions and all those things, right? Again, these are database concepts which we are telling the programmers, if you want to deal with all these issues, database people have been solving this for a while. So you may want to think about this as a transaction and solve those. But if enough of you complain in the future, maybe you will provide this in the operating system. Right now, many of you are not complaining, so we're kind of okay. But I suspect that we can't be in that state for too long. So eventually when you come for the stuff, this is how we'll help you. So we are sort of in this partnership mode for now, right? And again, you have the notion of deadlocks, and the second part was like we define the notion of deadlocks and how you might avoid it or prevent it or what have you, right? So before I go, actually I thought I had one more slide. So one of the question was, how do you, when you write a threads program, how do you know where you should put a critical, what is a critical section, right? How many of you understand like what is a critical section in your program? How do you go about finding that? That's actually right on the board, right? Let's say we have 3 threads, and you look at it, you say count equals 1. You look at your program, and it looks like there are one shared variable used in the 3 different threads, right? Does that mean that this is critical section?
No, it's only when you change them, right? It's only when one thread changes, it's going to make a change to that variable.
Yeah, but all of them are changing, right? They're all setting count to be different values.
Oh, you're changing.
Yeah, I'm changing them, right? So does that mean that they're all critical section? Yes?
It counts global, it's a critical section.
Oh, yeah, so this is a global variable. Somebody wrote a program, okay? Somebody wrote a program which has this stuff, and they give it to you and they say, I don't know anything about critical section. Since you're taking a course in operating system, can you fix this problem, right? So do you keep saying lock, unlock, right? You put lock and unlock, lock and unlock, right? Is that what you should do? Will that work as a first cut? You don't know what it's doing, but just protect everything, right? Is there a reason why you would do that? Yes?
Well, I mean, I guess as a first pass, it'd be a good thing to do it, because if you're writing to shared data, then you want to make sure that...
Yeah, I mean, it sounds like it's a thing you can do, right? Just protect everything, right? I mean, nothing could go wrong trying to be too protective, you hope. So you kind of put these things up, right? Is there a reason why you don't want to do that? Yes?
If count is used like as a loop variable or something below the lock and unlock, and so it changes it to 5, say in the third thread, it jumps back into the second thread and changes it, it may be dependent, or is that?
Yeah. So do you think what happens because of that? Do you think it'll slow down or?
It might not do what you want it to do.
Yeah, that's a good point, right? You don't know what the other person was wanting. By you putting a critical section, you are giving it some order, which may or may not be what they wanted, right? But then, without the critical section, their program was giving them garbage, right? Now it's giving them a different kind of garbage, right? I mean, right? Because without the critical section, you have no way of guaranteeing what you're going to get, right? That's the main argument that we had for the whole thing, which is if you just put it like this, the value of count could be anything, right? Because of the race condition, right? Now, by you imposing an order, it'll give you some order, which you understand that you're going to now have this particular order, but maybe that's not what the programmer wanted. But it's a buggy program anyway, right? But that's an excellent point, right? You may get something which they may not really want. Yeah.
It doesn't really matter anyway because you're writing three different values to it.
Mhm.
So whether the critical section causes those to come in one order or another, one of the values will be the final value anyway.
Yeah. So that's a excellent observation. That again goes to the fact that the original program was buggy to begin with, right? So you are to really fix it, right? So what do you tell your friend, right? You have to tell them your program is completely buggy, right? Because it cannot guarantee what it is, right? So what do you really want? Right? So you have to ask your friend, what do you really want? At this point, do you want one of them to stay? That means I need to create the particular order, right? If you don't, your program is very buggy because it can produce whatever results. And you can't just solve it by putting these stuff because it'll still give you some output which is predictable, but maybe that's not what the programmer wanted, right? I think that's what both of you are kind of saying, right? So so let's assume that they say, oh, we move past that problem, right? For some reason, right? Would putting all these locks still solve the problem as a first cut? Would it cause other problems? So what I'm asking is, would you randomly putting locking stuff, right? What are the problems it can cause, right? One is unpredictable results from unpredictable situation. What is the other one? Yes?
Slow the code down, you know?
Yeah, it'll slow it down, right? Because every time you do a critical section, you're going through depending on how these things go, right? You're slowing it down because it's no longer free reigning, right? You're creating some sort of order, right? So it can potentially slow the program down. So you as a programmer have motivation to make sure that you only lock certain things, right? So for the homework project 3, right, 2, you can solve the problem by locking the array anytime somebody modifies it, right? And you'll notice that your program is not going to be very fast, right? How many of you saw sort of like a linear speed up? As you had more threads, things kind of went faster and faster, right? The others didn't see it, or you haven't done that yet. You should, because it's not a very, it's not. I don't think it's a very complicated enough program, right? One thing you may want to do is like there's a printf at the end. When you're doing the timing, you may want to comment it out, right? Because the printf is a straight line code. It might make a slight difference, right? But not much. I mean, the code has enough scientific stuff that you may notice the stuff, right? You may notice it going faster, right? So you get the timing problem, right? Is there any other issue that you may cause? One is timing. One is the program could be unpredictable, right? What is the third thing that can problem that you may introduce? Yeah.
Deadlocks?
Yeah. So that's the whole thing about the last chapter, right? The deadlock chapter, right? Depending on how you're proceeding, right, you putting locking all the stuff would mean that you may get into a point where clearly when you had nothing, you had no deadlocks, right? Obviously, because it doesn't violate any of the stuff. But if you randomly start critical section, which in the deadlock terminology means that you're randomly holding resources, right? Whenever you lock, you're holding a resource, right? So if I randomly throw in all these locks, then I'm randomly I could potentially cause a deadlock, right? So it need not happen. So the solution is never I mean, unless the program is extremely trivial. I mean, I think this program would be extremely trivial because there's nothing. But in a regular program, you don't just go in and kind of protect all the shared variables. You want to know precisely what your program does, so then you can kind of know what could be locked. One for the notion of performance, right? The other is for preventing deadlocks, right? So have you ever wondered why Microsoft spends like all the human beings and all the time it takes to write PowerPoint, right? PowerPoint version 1 to the next, right? It takes like 3 or 4 years, right? How many of you thought that you can write PowerPoint if you just sat down and in a couple of weeks or something, make it go, right? Maybe not all the glossy stuff, but for the most part, right? But why do you think they're trying to get the last bit of stuff, right? Another example would be actually Photoshop, right? If you're working in Adobe, right? How many of you use Photoshop or one of those tools, right? Those tools don't come out every day, right? And if you look at the stuff from one version to another version, it's not like they change everything, right? I mean, there's slight modifications, but they spend a lot of effort, right? And this is one of the things where they spend a lot of effort, because they want to parallelize this stuff. If you get 2 cores, they want it to run twice as fast, right? You'll be happy if you go out and buy 4 cores, you run your Photoshop, if it did everything 4 times as fast, right? They're operating on lots of data, so this really helps, and it's not a trivial task. I mean, they may have like a few hundred people working on Photoshop, and they have to worry about this stuff. So if any of you feel, if it turns out that all of you feel that this whole thing is hard, that's perfectly fine. Ask any of those guys who work in Adobe or whatever, right? They'll tell you that this is very hard. It's very hard because now you have to exactly understand what your program does. The case I said where you just throw in some cases and your program works, doesn't work. The cases where you notice that something is going wrong, so let me put a lock here, doesn't work, right? It may work for you for some time, but then it bites you somewhere else because some things have changed, right? So you really have to understand what your program does. So in a lot of sense, I'm just pointing the mirror back at you and saying, when you program with these things, your program bugs will show up a lot more obviously, complicated fashion, right? All the notion of deadlocks and all those things it's your programming bug. Operating system may help you, but it's really your thing, and right? Is that it's not meant to say I have no responsibility, it's your programming kind of stuff, because like I said, it's all partnership. But you're basically facing the issue of how these two interact, right? I handed out the 2 exams, right, from last 2 years. Obviously, we don't have to follow that model. It might help you. I mean, it's actually on the web, right? So if you go to my homepage, you can see all the prior exams. That may be a good way to look at this. I actually printed out the, let me see if we can do this, right? The Java code for bounded buffer problem. It's in the newer version of your book, right? And if you look at that, it's mostly Java programs. I don't know if I need to go through the stuff. But what I want to point to you is some of the aspects, right? First is the notion of synchronized, right? If you call so if you don't know Java, then this may not help you. But if you know Java, if you make this stuff synchronized, right, that's a monitor, right? That means this particular call becomes a monitor. So that means any function within this object is a monitor. We could say explicit lock, right? So the insert function is a monitor. You don't make this synchronized because that's the one that's creating the object, so you don't have to do that. But this is monitor. So essentially, if you see the word synchronized, that particular stuff becomes a monitor, right? So when you write a Java program, it's very easy to use monitor. It's either very easy to use monitor, or it's so easy that you'll abuse it and make stuff monitors and you don't have to, right? Remember, if you make a monitor, that means only one thing can run through it, right? So you'll see a lot of cases where people throw synchronized, and you wonder why they had it. That's because they don't understand what this word is. They just throw the word in, right? But essentially, the synchronized means that that's a monitor. And if you look at the function, it's fairly trivial. And here's the wait function, right? So if you know Java, that's the try wait, right? That's essentially your monitor wait and notify at the bottom, very bottom, right? That's the one which signals the stuff, right? So the block is essentially the wait, and notify is when you do the signal, right? So in Java, for you to use a monitor, you call it synchronized, and to block on something, you call a wait, and to be notified, you call a notify. And it's the same as the monitor function. If there's nobody waiting, the notify is lost, right? From the homework assignment, right? I'll let you read through this stuff. If you know Java, then this is trivial to read. If you don't know Java, then I still think that this is easy to read. The last one function I want to show is the notion of how to create a thread, right? You have to make the object runnable. Okay. So this is how you create a new thread in Java, right? You call we'll see what the procedure, if you look at the procedure in a separate stuff. So you create a new thread, and then you do a start. Right? When you start a thread, it starts to run, right? And for the consumer thread, you call it implements runnable, right? If you say implements runnable, then it's potentially a thread. So in the main function, when you call a new thread with this function, with this object, then that means it's runnable, right? So in Java, creating a new thread and making this stuff is fairly trivial. Go to this particular application. If you have any trouble, send a chat or drop by this afternoon, right?